Okay, I'll just get started because I know people are eager to have time in the afternoon to work on their hackathon projects. And the first part of this tutorial is like really, well, all pretty simple, but it's really simple, so I don't think it'll be really detrimental if someone walks in late. A couple things to note are that so there are 4 Jupyter notebooks, but the first one uses R kernel. If you don't have your Jupyter notebook configured to use R kernel, you can just open the HTML version in a browser. So there's a folder within the directory that contains the tutorial that just has HTML versions of everything. You just open that in a browser and just follow along. Or you could open, I also saved an R script that just has all the commands. So if you have R Studio, you could just open this in R. Or if you have Jupyter Lab configured to be able to use the R kernel, you can just run the cells with me. But the HTML file should be usable because it has all the output and it's all pretty simple stuff. And then the third notebook is everything else is Python, so you don't have to worry. But the third one is probably the main thing. The ones with the prefix 2 are just like super quick. I'll just go through them. We won't run them because I didn't actually bring the brain data because I thought it'd be too much for people to download with our questionable internet. So we'll just like quickly just go through how we got the data into shape to use for the main analysis. So we'll start with the first notebook. So just an overview of networks, working with network data, visualizing it, and so on. Essentially, so we're first going to just go over network basics, visualize the network from that last study I told you about, and also visualize another network that might lend itself more to nice and informative visualization. And then in the next of notebooks, we'll just get the brain data into a nice format where we can look at inter-subject similarities really easily. And then the third one will test the relationship between social network distance and neural response similarity, and also visualize it. Oh, yeah. Okay. Is that big enough? Okay. So really simply,
Carolyn, it's on the GitHub, right, or not?
Oh, yeah, it's in the GitHub in the tutorials folder. Yeah. But essentially, a network is just a set of nodes or vertices connected by relationships or edges. These connections can be directed or undirected, so they can be things that are inherently directional and not necessarily reciprocated, like who emails whom, who asks for advice from whom. They could be things that are inherently reciprocated, like shared attributes, for example, who goes to the same school, that kind of thing. They can also be weighted or unweighted. As one question kind of touched on, so you could have sort of an adjacency matrix where all the elements are zeros or ones, so there's a connection there isn't between 2 nodes, or one where the value can fluctuate. And so I made a little toy network here to show you how to just manually construct a network from an edge list in iGraph, which is also a Python module for iGraph. The syntax is a little different, all based on the same C library. I think there's also a JavaScript version as well, but I've never used it. And so essentially we can make an edge list about maybe Luke's lab. It's familiar to a lot of you. So we can make a directed one, say who, at least in a formal sense, mentors whom in Luke's lab. And so we would make an edge list like this, where there's a connection going from Luke to Eshin, Luke to Andy, Luke to Jin, Luke to Emma, Luke to Daisy. And then after we create this edge list, we can just make it into an iGraph object. And then we can plot it after we execute the above cells. And we can see there's this directed network of connections from Luke to his lab members. And we could also look at connections that are undirected. So for example, who of these people works in the same building in Moore Hall? So this would be a full graph. So there's connections between every pair of people, and it would be undirected. So you'd see a network that looks more like this. But normally, of course, you wouldn't just manually enter in vertices or edges, right? You'd load in your data from a file, and usually you'd either load it in as an adjacency matrix, which would take a form like this, where you have, if it's an unweighted network, ones in the cells where there's a link between your nodes, or as an edge list that would look like this, with the first column being the source of a link if it's directed, and the second column being the target. And so instead of manually entering in our connections, we'll just read in an edge list of the reported friendships in an academic cohort. And this is actually the data from the last study that I just showed you. And it should be in the folder you're within if you've updated the GitHub repo for the tutorials. So we can see loads in as this directed edge list. Convert it to an iGraph object. You can see just like a set of 279 nodes with about 8,000 edges between them, and it's directed as indicated by this D here, and the nodes are names. They have anonymous subject IDs, which will be helpful later in relating this to the neural response data. It's simple to extract information about what edges in your network or what nodes are in your network. But before we go any further, I think you want to simplify the network to get rid of loops, which are just links between a node and itself. So these are cases where somebody nominated themselves as their friend. It would be interesting for some other line of inquiry, but probably not for what we want to do. Now we want to plot the data. And so first we can try just plotting it with like the default parameters. Just to forewarn you, it's going to look pretty hideous, and it's not going to tell you very much, but we'll sort of progressively clean it up. So if you just plot the graph, you just get this really hideous and uninformative jumble of shapes and labels. But we can make some easy tweaks to at least clean it up a little to reveal a little bit more about what the network looks like. So we can set the size of the vertices and the edges and the arrows to create less overlap and look less cluttered. Stipulate the edges as a higher contrast color. That looks a little bit better, but still kind of just a hairball, right? And then one thing you might want to do if you have a really densely connected network is cut down some of the edges. So here we could cut down all the edges that aren't mutual. So friendships that weren't reciprocally reported. So if I nominated Mark as a friend, but he didn't nominate me, we could get rid of that edge because maybe I was wrong about our friendship. I'm just misguided. So we can turn this into an undirected network, stipulating that the edges must comprise mutual ties, and it starts to look a little bit better. And you may be wondering, what's determining like where all the nodes appear in the graph, right? So by default, iGraph uses an algorithm called layout nicely, or a function called layout nicely, to sort of try and choose the right layout algorithm depending on the format of your graph, like how big it is, how dense it is, if it's directed or not, if it's a single connected component or not. So if there's different isolated communities that don't share connections between one another or not. One class of layout algorithms that works pretty well for relatively large graphs are called force-directed algorithms. And the sort of details of how these work are outside the scope of this tutorial, especially if we want to fit in a significant amount of stuff before lunch. But essentially, these kinds of algorithms sort of simulate the network as a physical system where the edges are springs, and you want to minimize energy in the springs, and also the nodes are kind of like electrically charged particles that when they get too close to one another, they repel one another. And so essentially what you end up with is a layout where there are pretty evenly spaced nodes, and they don't overlap as much as they might otherwise. And so there are a couple pretty popular ones, such as the Fretcherman-Reingold or the Kamada-Kwai algorithm. And so you can stipulate one of these in this layout function in order to yield just like a list of coordinates of where each node will appear in your graph. So we'll do that. We get this list of coordinates, and now we can plot the graph. And so it's looking a little bit nicer. More, even bigger, okay. It's bigger. And let's see. So I scroll too far. Okay. But a lot of layout algorithms will actually work best if you don't have isolates in your graph. So you can see we have this one lonely person over here who didn't have any reciprocated friendships. And so the other nodes are sort of pushed together more in our space than they may otherwise be. And so a lot of the time, if you're, when you're working with a graph, you might just want to look at the biggest connected components. We can get rid of this isolate, which is just the term for someone who's unconnected, by selecting only the vertices that have a degree centrality greater than 0, making a new iGraph object, and then getting the coordinates of those vertices. And then we end up with a graph visualization with slightly less overlap between the nodes, a little bit clearer, but is still probably not the most informative data visualization, to be fully honest. But we're sort of getting there, at least. And also, I think it's important to highlight that it's not necessarily informative to look at where a node falls in a visualization. A lot of people have the impulse to read into it. Sometimes you could just lay out the nodes randomly, in which case it might look like this. And so where a node falls in the space is inherently not meaningful. You could also specify a shape, lay them all out on a circle. Again, it's not necessarily meaningful where they fall. So I think it's just important to keep in mind, because a lot of times people have the sort of reflexive tendency to just interpret who's in the periphery, who's in the center. But in any case, so we've made a little bit of progress in trying to visualize what our network looks like. But here, our main goal is really just to sort of visually depict the logic of the study, that we characterized the social network or the friendships among a community, and then we had a subset of people come in and do something like fMRI study or something else sets them apart from the other nodes. And so for this purpose, maybe this layout is okay. We just want to show here we've characterized all these friendships between all of these people, this bounded community, had them come in and do a study. But it would be informative to highlight the people who did the study in the network. So we can just import a list of the people in the network who were participants in the fMRI study, like so. And so now we just have a character vector of IDs of people who participated in our fMRI study. And then we can just indicate that each vertex in our graph should be one color. So here, gray if they are not in this list of fMRI subjects, and another color here, tomato red. You obviously choose anything if they are in that list. And so we can assign that as a vertex attribute. So it'll now just be sort of permanently mapped to your graph object. And then we can plot it again. And now we see sort of, I guess, a little bit more helpful information about what the study comprised. And so I guess this visualization, I would say, tells you that you mapped out the connections between people in community. You had a subset of them do something else, or there's something special about them, but not much else beyond that. A lot of times you'd want to maybe visualize the sort of macro level properties of the graph, maybe by thresholding edges if it's a weighted network, and just showing only edges that exceed some magnitude. But here, our purpose is to show that we mapped out all these edges, so we wouldn't want to do that. Also, it's a pretty densely interconnected network. So in order to show you really quickly, before I move on to the next thing, how you might look at these kinds of things, we'll use a different network that is more amenable to looking at things like community structure. It might be more familiar to some of you than just looking at relationships between anonymously labeled nodes. So we'll use Game of Thrones books. This data set was actually the subject of a really kind of cute article in Math Horizons magazine a couple of years ago. And basically, the authors mapped out the network of one of the books, Storm of Swords. They've also done all the other books now. I think those are all available, and also the TV seasons, but I don't think those are available. And the edges are defined by whose name occurs within 15 words of somebody else's name. And the assumption is that if two names are co-occurring together in the text with that kind of proximity, then it's the case maybe they're being spoken about together, or maybe they're speaking to one another, or maybe they're hearing about the other person, so their stories are interrelated in some ways. So we're just going to load in this edge list based on Storm of Swords, this Game of Thrones book. I guess, how many people never watched or read Game of Thrones? Okay, so these will just be funny nonsense names to you, but hopefully for many of you, this will be more meaningful than like subject 1, subject 2, subject 3. I thought it would be less depressing than like another common reference point is like politics or something like that, but I don't really want to talk about politics. It's too dark, even darker than Game of Thrones. So now we've loaded in this edge list, and we can convert it to an iGraph object and just see what it looks like. And so you can see these are undirected ties. So there's no arrow connecting them between the characters. There are 107 edges, or rather nodes, 352 edges connecting them. And then the U and W just means it's undirected. The nodes have names, and it's weighted. So the nodes have, or rather each edge has a weight corresponding to how frequently the two names appear together in the text. And so first we can visualize this network, and maybe it'll be more meaningful to you than the first network because those are strangers and unidentified. So we'll also here scale the node size to a vertex attribute. So here we're going to set up this function where we just are going to be able to give a list of vertices and a minimum value for node size and a maximum value, and then it will return like a list of sizes for the nodes that fall between those two A and B values so that we can scale the node size accordingly. So for example, we can apply this function to an attribute like degree centrality, so how many edges a given node has, how many other characters connected to, and then just make the people who have the lowest degree centrality, so have the fewest connection to others, whatever we're going to give the function for A here, so our minimum size, and then make the people who have the largest degree centrality in our data set have the whatever we give this function for the maximum size. So we'll say 2 and 5. You can experiment with what looks best for you, and plot the graph. And it's hard to visualize it with everything blown up, but hopefully you're following along on your own computers. And so you can see it's like a little bit less densely connected, maybe lends itself more to experimenting with visualization here. It's a single connected component, so there's all the nodes can be reached from every other node in the network. But it's often the case that even within a connected component, you'll have a pretty modular community structure. So the component can be comprised of communities where there's lots of links within the community, not a lot of links between the communities, and we can try and visualize those. And so there are many community detection algorithms you can use. I won't go into detail here regarding those. We'll use fast-greedy algorithm, which maximizes modularity and is very fast, although network smalls probably doesn't matter. And then we'll just apply this to our graph. Oops. And then we'll make another vertex attribute that's the community membership. So if the community detection algorithm partitions our graph into like 6 communities where there's lots of connections within those communities, not a lot of connections bridging the communities, now we're going to assign each vertex or each node a number that corresponds to what community was that node assigned to. And then we can pass this, and then we can also map each community value to like a color name, so that we can color the nodes depending on what community they belong to. Does that make sense? So what you end up with is what you might expect. Sort of, if you have read the books or seen this show, you know that there's a lot of frustratingly disconnected storylines, like when is Daenerys going to get to Westeros? Like when are they going to get to the wall? And, you know, there's a lot of drawn out parallel storylines. Some of you would expect this sort of community structure. You can also highlight the community structure like this rather than just coloring the nodes, just by sort of marking them with silhouettes. It's basically the same information. And so you could just overlay the labels on the notes to see who's been assigned to what community, but because there's so many and we're in a relatively small space in the browser, probably just be a lot of overlapping labels, so we'll just look textually. So we can look, for example, here, who's in community 4 and who's in community 5. And you can see, for example, depending on how nerdy you are, that the community 4 has people whose storyline kind of unfolds together. So does anyone have a thought about who these people are? Yeah, the Watchers on the Wall, the wildlings, right? So these people are in their own little community, and then here's Daenerys and everyone in Essos, I want to say, yeah, whose storyline is sort of separate from everyone else. And so that's just to demonstrate how you can detect and visualize community in a network where those communities might be more meaningful to, I guess, some, but not all of you. So hopefully you can refer back to this if you want to do this with any of your own data. I know I'm going through it pretty quickly. And then one other quick thing I'll say before we transition to the brain data is that it's easy also to just extract information about nodes or edges in the network as well. So we can say, we only want edges that exceed 75. So names that were mentioned at least 75 times together. And if you do that, you see these are people who spend a lot of time together in the story, right? So Bran and Hodor, traipsing around in the woods together and so on. This probably seems reasonable to you. You can see who's a neighbor of a given node, so who's directly connected to a particular person. You could check what's the distance between two nodes. So what's the shortest path between two characters? You could check, has Daenerys met Tyrion yet? And the answer is no. Or rather, that's the value in the adjacency matrix, rather, not the shortest path. So 0, they're not connected. And also, we can see, for example, who's the highest in terms of degree centrality, who's the lowest. And so this probably fits with your intuition if you're familiar with these people. If not, bear with me, I suppose. So these main characters are connected to a lot of people, and then these individuals who are sort of more isolated, interact with less characters, have lower degree centrality, like Shireen. We're only spoken about. Yeah.
So there are different ways to do the clustering, and they usually give different outcomes. What ways did you use, and how did you sort of qualify what?
Oh, so I'm just using this as an example. So I just applied sort of arbitrarily fast food. I haven't looked at different things like label propagation and things like that. Others have. I think it's a really widely explored data set, but I guess I haven't done the work to answer that question.
And what clustering method did they use here?
I think the map algorithm, or actually I'm not sure. I just took their data and left it at that, just to sort of introduce some concepts really quickly. Yeah. And also we can look at strength, which is just weighted degree centrality. So basically add up all the edges that someone is adjacent to and see, for example, Tyrion is mentioned a lot. So this is essentially just the sum of all the interactions someone's involved in, whereas these other individuals, not so much. And then you can also, between a centrality, so Talia defined this for everyone, what's the frequency with which you're on the shortest path between two others in the network. You can see that certain characters that appear maybe in different storylines or that travel between different story arcs have relatively high degree centrality. So this is just meant to give you like a basic introduction you can refer back to how to sort of extract and visualize pretty basic network properties. And then the main thing, are we supposed to end at 12? This would probably only take like 10 minutes. Yeah.
So in your own data set where you essentially constructed the full class
No, we took anybody who would come. Yeah. As long as they weren't that one person who was not connected to me. No, that person didn't volunteer, but yeah, we didn't. We just wanted as large of an N as we could get, so we just enrolled as many as we could. That's a good question. So the next few data sets, you don't have to execute them. You probably can't because I didn't give you the brain data, but I just want to quickly show you how you would get just like a set of EPI runs or just like nifty volumes that you take from the scanner and get it into the format where it'd be easy to look at inter-subject correlations in the way that I showed you in my talk. So the first thing would just be, pre-processing, removing motion artifact, and so on, and like also regressing at other potentially like physiologically based sources of noise, like signal ventricles or local white matter and so on. And so that's just what's done in this 2A script, which I won't really go through because I think you probably already all know about pre-processing. Just sort of to give you full information, I've included these. And then the 2B notebook is just concatenating those pre-processed files across runs and then cleaning up the directory a little bit. So I don't think it's important to go through that. I just wanted to show you how data if you wanted to. And then the third, 2C, is just sort of taking this pre-processed time series and turning it into a structure that would be convenient to work with when relating the social network proximity data to the neural response similarity data. So essentially, we're just going to make a JSON file that will be a nested dictionary with like a key for each subject pair or dyad, and then values for all the different distances that describe them. So distance in the network, correlation distance between all of the different ROIs. Does that make sense to everyone? So I don't think I have to go through this. This is really just data munging, but that might be convenient. This is all using FreeServe for parcellation and Afni's Summa to sort of map things together. But yeah, this is maybe just useful as a reference, but I don't think it's particularly edifying for the purpose of this. And the third thing we want to do is combine these two kinds of data. So luckily, this is all using a Python kernel, using data you have available to you. So maybe this is the most meaningful and interactive part of the tutorial. It will be very simple because actually most of the analyses in the paper that I present at the end of my talk are very, very simple. So we're just going to read in the edge list. So this is using iGraph in Python. As I said before, you can use an R, Python, or JavaScript, whatever is most convenient to you. So we're going to load in that edge list, and you can see basically it's, I guess, like an adjacency list where it's just what edges exist between each pair of people in the network. And as before, we've removed the loops, so people who nominate themselves as friends, and we make an undirected network comprised only of mutual ties. Maybe I'll run this again, get rid of this. And then we're going to load in a list of our fMRI subjects because we only want to compute network distances between those people because it would be silly to include the others. And then now we're just going to make a list of all the possible unique pairs of subjects, and then read in a JSON file that you should all have that's just a dictionary where for each participant you have, I guess, another dictionary that's just like their time series data for each ROI. So you just have a bunch of scaled average or small magnitude within each of the anatomical ROIs. And so for each pair of people and the unique subject pairs that we find a few cells up, we're going to first the shortest path between the network. So what's the geodesic distance between these two people? We're going to add that to our dictionary describing these two people. And then also for each pair of people in the network, for every ROI that isn't like white matter or ventricle or something like that, And from the free surfer parcellation, we're going to extract the time series. And if one of the subjects is missing data for that RI, which sometimes happens when you do the coverage issues, for now, compute the correlation between those people. We're going to add some to dictionaries because it's really simple. And then we're just going to turn that into a pandas data frame since it's convenient for visualization. And visualize the average correlation distance, or the average z-scored correlation distance at each social distance in the network. And also I converted these to similarities from distances just because people told me they found it more intuitive to see. And so, if you were to zoom out as a figure like I showed you in my talk, does that make sense, everyone? And then the other thing I want to show you guys, I feel like I'm going really fast, but like, just if you want to refer to this later, having to internalize all the data. What I want to do is so you have to be, I guess, cognizant if you want to test if the one of these similarity values is significant because our data points are independent, right? People participate in the data. There are lots of ways to account for this. One way is permutation testing. You keep the structure of the graph same. So you can think about the graph diagram we made in the script. Remember all the fMRI subject red nodes, just shuffle the between a bunch of times and compute the similarity of times, and then count the proportion of times that the, for example, similarity among friends, and say the ventral striatum is higher in the real data than in this random. Is everyone? Couple of functions to do that is just shuffle the ID. And function that some more candidates, which we did earlier, pair of people, get the correlation distance between ROI, and get the distance between the network. And now we're going to save, we're just going to do 10 permutations because and we're just going to 10 times randomly shuffle the brain data across nodes who participate in our study, the structure of the network the same, and get the neural similarity data for this really computed version of our data set, and save it. And so I don't have maybe as fancy a computer as you. Actually take like a minute or two to do 10 permutations. But this is almost the end, I promise you. And then we'll just, only other two things we'll do is just compute the p-value for given y, and then visualize that distribution. So the way we do that is essentially, oh, I didn't. You can extract, the p-value for nodes at a given distance for a given area for our 10 permutations. For example, for the right nucleus accumbens, the similarity in the randomly permuted data never exceeded the real similarity, but it did 20% of the left nucleus. So it's one way to sort of do significance testing, and then you can also just plot the distribution of your these look a little unattractive here because we only have 10 permutations, but you can surmise how beautiful they might look were you to run many permutations. And so I know this is really fast. I just want to make sure you guys have lots of time to work on your hackathon projects. This is the last day, and also it's right before lunch. And so I thought if I just give you all this information, you can apply to find use to you when you're working on your own data, maybe in your hackathon or something like that. And so hopefully this has been at least useful, and I'm happy to talk more over things in more detail or into questions throughout the afternoon or lunch. Does anyone have any questions? Just hungry, eager to hack.